We were talking about what kinds of ionic compounds are soluble and what kind are insoluble. And we can use those solubility rules to help us identify precipitation reactions. So here we have a picture of a sink, and we've got this white stuff on it, hard water deposits, right? So hard water has calcium ions and magnesium ions in it, and those are naturally occurring, and they're actually good for you. But those can react with soap and form a gray curd-like substance or a bathtub ring. And so you can not only get, the hard water spots, but you also get this kind of scummy stuff. And that's from the reaction of soap with the hard water. So because you don't want that kind of stuff on your clothes, laundry detergents will contain sodium carbonate. And what the sodium carbonate does is it forms an insoluble compound with the calcium and with the magnesium, essentially removing those two ions from your hard water. So calcium ion plus carbonate ion forms an insoluble compound that becomes a solid, and it'll just get washed away with the water. So a precipitation reaction is defined here, a reaction in which a solid, also known as a precipitate, forms when we mix two solutions. So precipitate here is similar to how they use it in meteorology. Precipitation is like snow or rain. It's something that falls from the sky, right? When you have a precipitation reaction, it sometimes looks like there's snow falling to the bottom of the flask. So, dry throat. This is an illustration of mixing potassium iodide and potassium nitrate. Both of these compounds are soluble in water. And so initially it looks like we have a solution, just some water, and we're pouring it into more water because we can't see those ions. They don't have a color. So in the Ki solution, we've got separated potassium and iodide ions. In the potassium nitrate, we have potassium ions and nitrate ions. And so I think of metals as being masculine and nonmetals as being feminine. And so potassium here, I think of this as being a guy, and here's iodide, and iodide's a girl. And this is limited because we have to have positive and negative charges. So this is not a commentary on today's society by any stretch of the imagination. But we have to have a positive and a negative. So we've got a positive and a negative, and these guys are okay with each other, they're friends and stuff, but they're just, hanging out together in this solution. Same thing here with lead and nitrate. And so I think of this reaction flask as these guys going to a party, and now they're mixing and mingling with new people, right? So these guys like each other, they go to this party, these guys are okay with each other, they go to a party, they're not in a committed relationship or anything. So what happens over here is that lead and iodide meet up, and there's chemistry, right? These guys are like love at first sight, and so these are the people that after the party's over, they discover them on the back porch making out, right? They just totally left the party. They're literally stuck on each other, right? So they're forming a precipitate and falling out of the solution. And what happens to potassium ion and nitrate ion? They're still just mingling around in the solution. Okay? Now, why do lead and iodide form a solid? Well, that's as hard as why do Joe and Sally get together and not two other people, right? It's kind of hard to predict. But we do have those rules of solubility that help us to predict which ions are going to really like each other. Any questions? So when we look at precipitation reactions or possible precipitation reactions, we need to be able to predict what the products are. So this is how you would do that. This is the same reaction we were looking at before. So here's our original compounds, the potassium iodide and the lead nitrate. And what we want to do is we want to identify what are the ions in those compounds. So potassium iodide has potassium ion and iodide ion. Lead nitrate has lead ions and nitrate ions. And so if we think, and they're even kind of color-coded here, blue and pink, guy and girl, what if they swap partners, right? So what if potassium and nitrate get together? Well, we can tell from the solubility rules, potassium and nitrate compounds are always soluble. You could say that potassium just doesn't get into relationships, right? It's not into commitment, and neither is nitrate. And so they're just going to keep floating around. But lead and iodide will form an insoluble compound. And so that will be our precipitate that falls to the bottom. If there is no precipitation, then there's actually no chemical reaction. So every time somebody holds a party, does somebody get into a committed relationship? No. Sometimes, but not all the time. When you mix two aqueous solutions, you do not always form a precipitate. So here, if we mix lead iodide and silver chloride, let's go down here. So there's potassium and iodide and sodium and chloride. And so we look at the possible combinations, and that would be sodium with iodide or potassium with chloride. First row on the list of solubility rules says that sodium and potassium are always soluble. They're not going to get into a relationship with anybody. So these two possible new compounds are both soluble. So really what's happened here is we have just mixed two solutions together. Nothing has really changed. These guys were separated as individual ions before. The only thing that's changed is now all four ions are mixed together. But we didn't create a new substance. So this is a physical change, because definitely something is different. They're jumbled up together now. But it's not a chemical change because we have no new substance being formed. Any questions? So here are guidelines for writing equations for precipitation reactions, and this is a skill that you should be able to do. And I'll read through these and then we'll do some examples. So we start by writing the formulas for the two reactants, and you start to write out the equation. And so below the equation, write the formulas for the products that could form when you swap the ions. Then look at the solubility rules to see if either of those products is insoluble. If all those products are soluble, then on the right side of the arrow, you just write no reaction, and you're done. So we always kind of hope that that's going to be what the problem is, but it only happens occasionally, because mostly we want to get you to practice. If any of the products are insoluble, then you have to write the whole equation. You write the formulas for all the products, and you put an S for solid after the insoluble one, an AQ for aqueous after the one that's soluble, and then you balance the equation. So let's see how that works out in a real example. These examples give us the names of the compounds instead of the chemical formulas. Gives us a little extra practice on the nomenclature. In an exam situation, you'd be given the formulas for the reactants. So write an equation for the precipitation reaction that occurs, if any, when ammonium chloride and iron 3 nitrate mix. So here we need the chemical formulas for the two reactants. The reactants are ammonium chloride and iron 3 nitrate. These are both ionic compounds. When we write the formula for an ionic compound, we need to look at the ions first with their charges. So ammonium chloride. Ammonium is NH4 plus because we memorize it. Chlorine comes from chloride. And how do we identify the charge on a chloride ion? -1, because you start at the periodic table with the noble gases is 0 and you move 1 to the left, so that's -1 for chlorine. So now that we have these two ion formulas and their charges, we can figure out how many of each of them to make a neutral compound. This one's +1, that one's -1. One of each ion stuck together will make us a neutral compound. So NH4Cl. And then the other one is iron 3 nitrate. So iron is Fe, because we memorized that. The Roman numeral tells us what the charge is. So this is Fe3 plus. And then nitrate ion, we have to memorize. It's NO3 minus. So then we need to put these ions together. And after a while, you can just kind of see it, but I think some of you are not there yet. So what I'm doing is I'm drawing out extras of these because I only had a -1 charge, and there was a +3 over here. I need a total of -3 charge to balance out the +3, and so I'm just drawing nitrate ions until the charges match up. And this tells me I need 3 nitrates. So the formula for this one is Fe, and that's a polyatomic ion, so I need to put shrink wrap parentheses around it, and a 3 on the outside. Okay? So those are my reactants. And now what I want to do is predict the products. So let's get rid of these extra guys. What I'm going to do is I'm going to say, well, what if these two couples swap partners, right? Let's see if ammonium and nitrate hit it off. Let's see if iron 3 and chloride precipitate. Why can't I see if ammonium and iron 3 form a precipitate? They're both positive charges. Our compounds have to be neutral. There has to be a positive ion and a negative ion. It's just electrical charges, they just work that way. So I'm going to write these guys under my equation over here. So here's NH4 plus with NO3 minus and Fe3 plus with Cl minus. It doesn't matter if you put ammonium and nitrate first or Fe3 and chlorine first. What does matter is that in these pairs, we always put the positive ion first and the negative ion second. Now we need to go to the list of solubility rules and look at the ions that we have. Well, let's start with ammonium. If we start down that table, if you have it in your notes, go ahead and look at it, or if you can imagine it on the whiteboard in your mind, right? Ammonium is in that first line with sodium, potassium, and lithium. Ammonium compounds are always soluble. So we don't have to look any further. This one's going to be aqueous. I'm not going to write it down yet because if this one is also aqueous, then I don't have to do anything else. So I'll just wait until I have to write the formula. So over here we have iron 3 and we have chloride. And so you go down that list again. And the first ion you're going to come to is the chloride ion. Chloride, bromide, iodide are together on a line. Those are generally soluble with some listed exceptions. This is not one of the exceptions. So that means that this is also a soluble compound. So this is also aqueous. So what does that mean? No reaction. And as if no reaction isn't short enough, oftentimes we'll just write NR for no reaction. So these compounds mixed, but they did not form a precipitate. So all they did was mix. And so that's our equation. Any questions? Let's do another one. Look at sodium hydroxide and copper 2 bromide. So we got sodium hydroxide and copper 2 bromide. Again, we need to look at the ions in these compounds so that we can write the chemical formulas. So sodium hydroxide, sodium is Na+. It's in group 1. It's got +1 charge. Hydroxide is OH- because we memorize it. And then over here we've got copper 2+ and bromide. The Roman numeral tells me the charge on the copper. Bromide is -1 because it's in group 7. Right? If you start on the periodic table counting 0 at group 8 and go backwards, -1, -2, -3, you'll get the charge on the anion, and so this is -1. So then I'm going to combine these two ions in such a way that their charges add up to 0, and so for this one it's just going to be NaOH. With this one, copper has a +2 charge, and bromide is only a -1 charge. So I'm going to need 2 bromides to make a neutral compound. And then I'm going to look and see, well, what happens when these guys mix it up at this party? We're going to check out sodium with what ion? Bromide. Sodium came with hydroxide. We know that they're not into some long-term relationship, right? Because they were soluble when they came in. So we're going to see how sodium and bromide get on together, and then how the other two get on together. So we're looking at sodium with bromide ion, copper 2+ with hydroxide ion. Will sodium bromide be soluble? Yes. Because that first line takes care of a lot of things, right? Sodium, lithium, potassium, ammonium, anything with that in there is soluble. So this is soluble. And then we have to look at this one, Cu2+ and hydroxide. And we start in the table and we look down at the rows and we get through the whole top part and we don't see hydroxide or copper ion. Then we get into the bottom part. Those compounds are generally insoluble with some exceptions. So hydroxide compounds are generally insoluble. This is not one of the exceptions. So this is going to be a solid. So I do have to finish out this equation. So here I've got +1 and -1 again. I can just put those two together. And this one's aqueous. And then over here, I'm going to need 2 of these guys to balance the charge on the copper. So I'm going to put parentheses around them and put a 2 on the outside, and I'm going to mark that as a solid. So making the compound formula from those ions, that is something that was in Chapter 3, which is on the exam today. So if you have any questions about that stuff, it would be good to ask. What else do we need to do? We need to balance the chemical reaction. So I'm going to try to kind of illustrate it on this one. So we had written 2 bromides earlier because for every 1 copper, there was 2 bromides, right? And let's do the same thing over here. So writing them out like this can help us to see what's going on. We have polyatomic ions here, and they're staying together, right? Hydroxide is a combination of 2 elements, but it stays together as 1 ion. We have hydroxide here, we have hydroxide over there. Hydroxide doesn't fall apart into oxygen and hydrogen. So it's easier to balance the polyatomic ions as whole polyatomic ions instead of looking at hydrogens and oxygens separately. So I like to start at the beginning. So over here, I have 1 sodium ion. And on the right side of the equation, how many sodium ions? Also 1. So that's good. I have 1 hydroxide here. How many hydroxides on this side? 2. Well, I need to fix that then. So I can fix that by putting a 2 in front of the sodium hydroxide, which means I'm going to have 2 sodium ions and 2 hydroxide ions, right? We already looked at sodium. Did this mess up the sodium? Yes, it did. So let's go back and fix that. Now we have 2 sodiums and only 1 over here. So we need to put a 2 in front of that one. So we'll have 2 sodiums, and then we'll also have 2 bromides. Okay, so we got sodium hydroxide straightened out. Let's look at copper. We have 1 copper ion here, 1 copper ion there. That's all good. 2 bromides here, and 2 bromides over there. And ideally, we should put state symbols on these guys. Those are aqueous because those are the solutions that we're mixing together. Any questions?